Hello friends, Professor T. N. Oza here. Good morning to all of you. In this new video, we will be studying the fundamental properties of gaseous state of matter, the simplest phase of matter. We will derive a number of relevant equations and the application part will be discussed in the next video. So let us begin with the physical states of matter. As we all are familiar, right from our school days, gas, liquid, colloidal state, and solid state. These are the main physical states or phases of matter. The plasma state may also be regarded as the fifth state of matter. Then empirical generalizations. Much before the mathematical equations were derived, some generalizations were enunciated by Robert Boyle as above at 1662, Charles 1787, Grahams, Dalton, Avogadro, Gay-Lussac. These generalizations were enunciated on the basis of experimental results. Their mathematical formulations, that is gas laws, were later developed by Koenig, Clausius, Maxwell, Boltzmann, and Bernoulli. So let us begin with the postulates of kinetic molecular theory of gases. A gas consists of tiny particles called atoms or molecules, which are discrete and ceaselessly moving randomly in all possible directions, x, y, z, colliding with each other and also colliding with the walls of the container vessel. When collision occurs, it may be elastic, that is no exchange of momentum between colliding molecules, that is ideal gas behavior, or collision involving transfer of kinetic energy, that is non-elastic collision. Perfect gas behavior is not like this. These particles are incompressible and their volume is negligible as compared to the volume of the vessel in which their gas is contained. Being ideal, the molecules neither attract nor repel the fellow molecules. Impact of the molecules on the walls of the vessel exerts pressure. Finally, the behavior of ideal gases can be described following the laws of classical mechanics, particularly Newton's second law of motion. Then let us talk about ideal versus non-ideal behavior. Most of the laws pertaining to the behavior of gases, including thermodynamics and chemical kinetics, have been formulated assuming ideal behavior. In actual practice, no gas is ideal or perfect behavior-wise, but non-ideal or real or imperfect. However, at high temperature and very low pressure, the particles are widely separated from one another and satisfactorily follow ideal behavior laws. Furthermore, the mathematical equations which apply to the behavior of ideal gases can be suitably modified to suit the real gas behavior. Next, we proceed to the pressure of an ideal gas. How is pressure generated actually? So let us assume that n molecules of an ideal gas of molar mass m, capital M, and individual mass small m are contained in a cubical vessel of edge L, that is volume V equal to L cube. Further, the molecule of mass small m is moving in the x direction at a velocity u, and after traveling the distance L and hitting the wall of the vessel, it is turned back with the same velocity, hits the opposite wall. This continues. The frequency of elastic collision therefore is 1 over time elapsed, that is 1 over delta t equal to 1 over distance over velocity equal to u by L. The resulting rate of change of momentum in x direction is given by del Px over del T. It comes out to be 2mu square over L. Supposing that the molecule is moving in all possible directions, x, y, and z coordinates, at respective speeds u, v, and w, we can define u square plus v square plus w square as c square. This can be derived, this can be proved also. We can write the change in momentum as follows. Del P over del T equal to 2mc square over L. Summing the contributions of all the molecules, we can write del P total over del T equal to 2mn over L, summation 1 to n Ci square. Defining mean square velocity, Cr square equal to summation 1 to m Ci square over capital M, which is the number of molecules. It leads to del P total over del T equal to 2mn over L multiplied by Cr square. The rate of change of momentum is the force F according to Newton's second law, and force per unit area, that is F over 6L square, where total area is taken as 6L square. It is defined as pressure. Therefore, P equal to F over 6L square, putting the value of F 2mn over L multiplied by 1 over 6L square into Cr square, comes out to be 2mn 6L cube into Cr square, or P becomes equal to 1 over 3V mn Cr square. Equation number 7. In this equation, the root mean square velocity Cr or Crms is defined as summation 1 to n Ci square over n under root. Equation 7 can also be written as the kinetic gas equation. Now we can write value of V as 1 over 3 mn Cr square equal to 1 over 3 mn C square. For simplicity, we are writing Cr square as C square, just for matter of convenience. So derivation of various gas laws from kinetic equation we have just discussed. First, Wiles law. Using the kinetic gas equation, PV equal to 1 over 3 mmc square. This can be modified as 2 over 3 into half mmc square. It means 2 over 3 into kinetic energy. As you know, with rise in temperature, velocity c of gas molecules increases. It is possible to define temperature T in terms of kinetic energy, which varies as c square. It implies, therefore, that at T equal to constant, PV equal to 2 over 3 into half mc square per molecule equal to constant. Evidently, PV equal to constant at T constant, and this is the Boyle's law in mathematical form. It means P is proportional to 1 over V at T constant. Isotherms can be made to show this pictorially. Second, the Charles law. Let us consider the kinetic gas equation again. PV equal to 2 by 3 into half mmc square. For a definite quantity of gas, capital N becomes constant, and small m, which is mass of the molecule, is also a constant. As we know, kinetic energy varies with absolute temperature. Therefore, at constant P, V is proportional to T under P constant. Thus, we can conclude that at constant pressure, the volume of a definite quantity of gas is proportional to the absolute temperature T. Now we pass on to Avogadro's law. Writing the kinetic gas equation for any two species, that is P1 V1 equal to 2 by 3 into half m1 n1 square c1 square, and for the second p2 v2 equal to 2 by 3 into half m2 n2 c2 square. If both the gases are held at the same pressure, that is P1 equal to P2, and equal volumes are taken, V1 equal to V2, and their temperature is also the same, that is T constant, then we can conclude M1 C1 square equal to M2 C2 square. Obviously N1 equal to M2, that is number of particles in both the gases will be the same. It means equal volumes of any two gases of molar masses M1 and M2 held at equal temperature and pressure contain equal number of molecules and at NTP 0 degree Celsius temperature, 1 atmosphere pressure, and this corresponds to 22.414 cubic decimeter of any gas which contains 6.022 into 10 to the power 23 molecules. This has been taken as Avogadro number, symbol Na. Then M1 N1 over M1 equal to M2 N2 over M2 equal to n number of moles. Now we can write the ideal gas equation as follows. At T constant, V proportional to 1 over P, Boyle's law. At P constant, V proportional to T, Charles law. At constant P and T, V proportional to N, Avogadro's law. Here N indicates number of moles. Obviously, V proportional to N T over P, putting a proportional T constant, or V equal to nRT over P, or PV equal to nRT. For two different gases, for the same gas under two different conditions, P1 V1 equal to N1 RT1 and P2 V2 equal to N2 RT2. This is the ideal gas equation. Alternatively, for 1 mole of an ideal gas, N is 1, P1 V1 over T1 equal to P2 V2 over T2. Next we pass on to Graham's law of diffusion. Again using PV equal to 1 over 3 mnc square. C is under root 3 PV over mn equal to under root 3 P over rho. Rho is density of the gas. Evidently, the rate of diffusion C is inversely proportional to the square root of density rho, which is defined as mass over volume. Dalton's law of partial pressure. Let us suppose that several ideal gases are contained in a rigid vessel of constant volume V at temperature T. Then, for each gas, we can write partial pressures as follows. PIV equal to NIRT. It means partial pressure PI proportional to mole number Ni. Evidently, total pressure P total equal to P1 plus P2 plus P3 plus so on. This is Dalton's law of partial pressure. Translational kinetic energy ET of ideal gas. Using earlier equation, PV equal to 2 over 3 into half mmc square equal to 2 over 3 ET. ET is kinetic energy. And we also know PV equal to nRT equal to 2 over 3 ET. It means ET equal to 3 over 2 nRT for ideal gases. And we know C square is proportional to T. It means C, velocity is under root T. Velocity C is proportional to under root T, temperature. According to equation, this is equation 14. Velocity C becomes 0 at T equal to 0 Kelvin. That is, motion of molecules ceases at absolute 0 temperature. This is just an assumption because absolute 0 cannot be attained. So this is the speculation or theoretical extrapolation of the graph. Average translational kinetic energy of one molecule of gas is given by epsilon T, which is equal to ET over Na. Na is Avogadro number, equal to 3 by 2 RT Na equal to 3 by 2 KT. Small k stands for Boltzmann constant. 1.38 into 10 to the power minus 23 joule per Kelvin per molecule. Here capital R stands for universal gas constant, 8.314 joule per Kelvin per mole. Avogadro's number Na stands for 6.022 multiplied by 10 to the power 23 per mole. Other units of the gas constant are derived as follows. R equal to PV over NT. Putting the dimensions, 1 atmosphere, 22.414 dm cube over 1 mole, 273.15 Kelvin. It comes out to be 0.08206 liter atmosphere per Kelvin per mole. Another unit of R can be derived as PV over NT. Putting the value 1.01325 into 10 to the power 5 Newton per meter square multiplied by 22.414 into 10 to the power minus 3 meter cube over 1 mole and temperature 273.15 Kelvin. It comes out to be 8.314 Newton meter per Kelvin per mole. This is written as 8.314 joule per Kelvin per mole. Joule means Newton meter. Note that ET is independent of pressure and volume but dependent on temperature. For example, for a gas, ET 25 degrees Celsius is 3716 joule per mole. Then at 50 degrees Celsius, the value becomes 7432 joule per mole. And for one molecule, it comes out to be 6.17 into 10 to the power minus 21 joule per mole, per molecule, not moles. Now we learn about the types of molecular velocity, concept of variable velocities. In any assemblage of gas phase molecules, owing to the random collisions, the concept of uniform velocity does not hold good. Instead, there is a distribution of velocities, say between C and C plus dc. dc means infinitesimal change. For the sake of simplicity, three kinds of molecular velocities are recognized. Let us assume that N1 molecules possess velocity C1, N2 molecules possess velocity C2, N3 molecules possess velocity C3, and so on and so forth. Then we define the average velocity as sum of NiCi terms divided by sum of Ni terms. The root mean square velocity has a different equation. It is given as the sum of NiCi square terms divided by sum of Ni terms. The square terms is under root taken. The most probable velocity is defined as the velocity possessed by maximum number of molecules. Using Maxwell equation, the following formulae have been derived. Most probable velocity is 2RT over m under root. C average is 8RT over pi m under root. Root mean square velocity is 3RT over m under root. Here m stands for molar mass, capital M. Small m, if used, then R is replaced by Boltzmann constant. It can be shown that CR ratio C average ratio C most probable is equal to 1 ratio 0.92 0.82. Similarly, C average over C most probable ratio is 1 ratio 0.886. The following figure shows most probable velocity, average velocity, root mean square velocity, Number of molecules is shown along vertical axis. Velocity distribution is shown along the horizontal axis. So this diagram is illustrative of the concept. Then let us do some numerical problems. Calculation of temperature at which the average velocity of O2 gas will be equal to the average velocity of H2 gas at 20 degrees Celsius or at 20 Kelvin. Two different problems. 20 degrees Celsius is not the same as 20 Kelvin. The solution, average velocity we calculate using the formula under root 8 RT over pi m. It means the average velocity is proportional to under root T over m. Given T for H2 is 20 degree Celsius, it means 293 Kelvin. We have to find out temperature for O2 gas by putting the values of different parameters. We find temperature for O2 is 4688 Kelvin. And for the second problem, where temperature of O2, temperature of H2 is 20 Kelvin, we calculate temperature for O2 is 320 Kelvin. Let us define two new terms, expansivity and compressibility of ideal gases. At constant pressure, the expansivity alpha, whose unit is T inverse for an ideal gas, is defined as follows. Alpha equal to 1 over V, del V over del T at constant pressure, and it comes out to be 1 over T. At constant temperature, the decrease in volume V with increasing pressure P is defined as the compressibility beta, unit P minus 1. So beta is defined as minus 1 over V, del V over del P at constant T, which comes out to be 1 over P. The proof has been shown here. PV equal to nRT, it means V equal to nRT over P. Differentiating this equation, V equal to nRT over P, with respect to T at constant P gives del V upon del T, hold P and N, equal to nR over P equal to V over T, because V is nRT over P. Hence alpha is defined as 1 over T. Again differentiating V with respect to P at constant T gives del V over del P at holding T and N. It comes out to be minus V over P. Hence beta is 1 over P. Note that beta is positive, but a negative sign is put for decrease in V with increase in pressure. Thermodynamic derivation of ideal gas equation PV equal to nRT. Writing V is a function of T, P and N, and taking partial derivatives, we have total derivative PV equal to del V over del P holding T and N dP plus del V over del T holding T and N dt plus del V over del N holding T and P dN. From Boyle's law, PV at constant T and N equal to K, so that V equal to K over P. Similarly, del V over del P holding T and N is equal to minus K over P square equal to minus V over P. Using Charles law, P and N constant, V equal to KT, so that del V over del T holding P and N comes out to be K or V over P. Again at constant T and P, V proportional to N or V equal to K prime N. So del V over del N holding P and T comes out to be V over N. Substituting these equations in the main equation yields del V over V equal to minus dP over P plus dt over T plus dN over N. Integration yields log V equal to minus log P plus log T equal to log N. Rearranging, we get ln V equal to ln P. There is a small mistake in the earlier equation. It is ln T plus ln N. By mistake it has been put as equal. The equal sign should be replaced by positive sign, plus sign. So taking anti-log both sides, we get PV equal to nRT, ideal gas equation. Questions for revision. Question 1. Write expressions for the three kinds of molecular velocities of ideal gases. Second question reads, what are the main deficiencies of ideal gas equation PV equal to nRT? Hint, it ignores volume of gas molecules. And secondly, it does not recognize the van der Waals attraction between the molecules. Question 3, write the corrected gas equation. How is it obtained? Hint, the ideal gas equation is PV equal to nRT. In the van der Waals equation, pressure correction replaces P by P plus N square A over V square, and volume correction replaces V by V minus NB. Here A and B are van der Waals constants. A has units of liter square atmosphere over mole square, and B has the unit of liter per mole. Question 4 reads, 1 mole of CO2 gas is stored in a rigid vessel of volume 1.30 liter at 45 degrees Celsius. Given that A equal to 3.59 unit and B equal to 0.0427 unit, we have to find pressure P. Just by putting various values in the equation, P equal to nRT over V minus NB minus N square A upon V square, simply by putting the values of N, R, T, V and the van der Waals constants, we can calculate the pressure is 17.67 atmosphere. Question 5. Calculate temperatures T1, T2 and T3 corresponding respectively to the three velocities: root mean square velocity, average velocity and most probable velocity, when each velocity is equal to 1600 meter per second for oxygen gas whose molecular mass is 0.032 kg per mole. Numerical can be solved very easily because CR equal to under root 3 RT 1 over M, which is 1600 meter per second. It means T1 equal to C square into molar mass of oxygen over 3R. In this manner, we find T1 equal to 3284 Kelvin. Exactly in the same manner, we can calculate T2, which is 3870 Kelvin. We can calculate T3, which is 4926 Kelvin. If we want to calculate such velocities for other gases, H2 for example, then the molecular mass has to be used differently. Alternatively, we can find temperatures at which different gases will reach equal velocities. For example, we have to find the temperature at which the velocity of oxygen gas will be the same as the velocity of H2 gas at 20 Kelvin. So we can use the equation under root T1 over M1 is under root T2 over M2. Putting the values of T1, putting the values of M1, M2 and P1, we can find T2. Other question reads, derive equation of state PVT equation for real or imperfect gases. So we begin with the statement, ideal gas equation derived on the basis of molecular kinetic theory suffers from two serious limitations. Firstly, it treats gas molecules as point masses, thereby ignoring their actual volume, which is an incorrect supposition. In fact, if the volume of the vessel is V then the volume available for the movement of molecules of for n mole gas will be V minus NB. In this, B is called the excluded volume per mole of the gas, and its value comes out to be 4 times the volume of 1 mole of gas molecules. Its derivation is shown with reference to the following figure. Legends in the figure: d by 2 equal to radius of the rigid sphere molecule, d equal to radius of the exclusion sphere shown by the dotted circle or a pair of molecules. This is the diagram shown, everything is explanatory, self-explanatory. The dotted line shows the excluded volume. Volume of one rigid sphere 4 by 3 pi t by 2 or cube comes out to be pi d3 over 6. Volume of exclusion sphere is 4 pi d3 over 6, that is 4 times the volume of the molecule. The excluded volume, also called co-volume per mole of the gas, is multiplied the earlier thing by Avogadro number. Compressible volume for n mole of gas is V minus NB. The excluded volume V has the unit of liter per mole. The second serious limitation of the molecular kinetic theory of gases is that it ignores intermolecular attractions. The molecule present somewhere in the mist, see figure marked A, experience no net attraction from the neighboring molecules because they are being actually pulled towards all angles. However, the molecule which is just about hitting the wall of the vessel marked B in the figure is being retarded or pulled backward due to inward force of attraction by the neighboring molecule. As a result of the act, the observed pressure PO is lesser than theoretical pressure PT by PI, which is called internal pressure. That is PT equal to P0 plus PI. Model for pressure correction has been shown. Calculation of PI, internal pressure. The force of attraction exerted on the molecule, which is just going to strike the wall, is directly proportional to the number of molecules present per unit volume of the bulk sample. This is related to the density of the gas rho and inversely proportional to the bulk volume V. Further, the internal pressure PI is also proportional to the number of molecules per unit volume of gas which are about to strike the wall at any time, any instant. Therefore, we can write PI is proportional to rho square or 1 upon V square. It means PI equal to A upon V square. A is constant. On molar scale, PI equal to A n square over V square. The proportionality constant here depends on the nature of the gas. Its unit is derived as follows. It comes out to be liter square atmosphere over mole square. Now we can write the van der Waals equation as follows: PO plus A n square over V square in the second bracket, V minus NB equal to nRT. For ideal gases, A equal to B equal to 0. Here I have collected some values of A and B for a few gases. It can be seen, larger the molecule, larger the value of A and B. When the density of the gas is quite high, the pressure correction term An square over V square can be neglected, and equation gets modified as POVM equal to RT plus POB. Here Vm is the molar volume of the gas. At moderate pressure, volume correction B can be left, and equation becomes POVM plus A upon Vm equal to RT. It means POVM is greater than RT. Here some graphs have been given. You are expected to learn these graphs and draw conclusions therefrom. Now we pass on to collision parameters. Collision diameter, collision frequency, collision cross section, and mean free path. Collision diameter. The distance between the centers of two rigid spherical colliding atoms when at their closest point of approach is called the collision diameter, symbol D. It has been shown in the figure. Collision number, symbol Z. Number of collisions suffered by a molecule in unit time, unit volume. Collision cross section. It is defined as pi d square, where d is the colliding distance. Collision types: elastic collision, non-elastic collision, perfectly non-elastic collision. Formulation of collision number. Let us assume that the number density of gas is rho, collision cross section area is pi d square, and a molecule is moving at an average velocity c average. Then the number of molecules with which it collides in unit time per unit volume is given as follows: Z1 equal to under root 2 into pi d square into c average into rho. The under root 2 factor comes from a statistical consideration of molecular motion. The total number of molecules colliding per unit time per unit volume is given by under root 2 multiplied by pi d square multiplied by c average multiplied by the rho square. For collision to occur, two molecules are involved. Evidently, we have to divide the earlier equation by half. Multiplied by half, not divide. The equation becomes 1 over under root 2 multiplied by pi d square multiplied by c average multiplied by rho square. For collision of molecule type 1 with molecule type 2, there is slight difference in the equation. It is 1 over under root 2 multiplied by pi d square average into c average into rho 1 into rho 2, v to rho 2. Here rho 1 and rho 2 are different gas densities, and d average has been taken as d1 over plus d2 over 2. Average value of d for both type of molecules. From gas equation, PV equal to nRT equal to n Na kT equal to nkt, and rho is actually P over kT. Thus we can formulate Z1 and Z11 again using P over kT in place of rho. Units of Z1 and Z11 are shown. They are second inverse and second inverse over meter cube. Mean free path. A very useful collision parameter in industrial vacuum system is called the mean free path, which is defined as the mean distance traveled by the gas molecule between successive collisions. It is defined as lambda equal to C average over Z1. As we know, we can put the values of C average and Z to find the equation for lambda, which is C average over Z1 equal to KT over under root 2 into pi d square into P. Here we have taken an example of numerical problem. Oxygen gas, molar mass 0.032 kg per mole, collision diameter 3.61 into 10 to the power minus 10 meter, temperature 298 Kelvin, pressure 1 atmosphere. So we have to calculate various parameters. Mean free path, lambda equal to KT over under root 2 pi d square P. The result comes out to be 70.1 nanometer. At very low pressure, the value is quite high. Mean free path is longer, much longer, 5.33 into 10 to the power minus 2 meter. We can also calculate average velocity under both conditions. It comes out to be 444 meter per second. Collision number calculation, it comes out to be 6.33 into 10 to the power 9 per second. Collision frequency between like molecules, it comes out to be 7.80 into 10 to the power positive 34 per second per meter cube. Number of moles of collision comes out to be 1.30 into 10 to the power 8 mole per liter per second. Here I have given some advice for the learners. Note down all important equations along with the units of various parameters. Draw different PBT diagrams, explain their significance, solve different numerical problems given in your textbooks. Make a summary note of definitions of important terms. Keep in mind that no ideal gas exists. All gases are real or imperfect. Under very low pressure conditions, their behavior may be considered as ideal, near ideal. Try to make computer simulations of molecular motions, collisions, absolute volume, and isotherms, PV isotherms. Do self-evaluation. Thank you very much for watching. Please like, share, and subscribe, please. Myself, Dr. Trivedi Narayan Oza, retired professor of chemistry.